Have you ever thrown a Frisbee forward with some spin and been surprised by it going up or moving to the left or right? This study was done to analyze forces on a Frisbee to determine how spin affects Frisbee motion. The model geometry used was a Frisbee of radius 0.13 meters with curved sides as seen in the picture. In some of the solutions, the Frisbee was spun clockwise at different rates with respect to the forward velocity. A channel around the Frisbee was designed with an inlet velocity to mimic throwing the Frisbee at a 5-degree angle of attack. The channel was designed with a large enough domain size to show the full effects of the flow over the Frisbee. Incompressible laminar flow was used after calculating the Mach number and Reynolds number to be small enough to make those assumptions. Shown on the slide are three-dimensional partial differentials of Navier-Stokes equations used by the model and a three-dimensional continuity equation. The gravitational force was neglected because the study is looking at the difference in lift, drag, and force from the Magnus effect, which do not depend on gravity. Of course, gravitational effect the total trajectory, but since the focus of the project is the effect of the spin on the forces, it was decided that gravity could be neglected and these equations would be used. A mesh study was done on the model without spin, comparing momentum balances, lift, and drag, and chosen when the lift and drag values converged and the momentum balances were close to zero. Shown above is the final mesh, which is most refined on the edges and bottom of the Frisbee and slightly less refined on the channel. Shown here are the calculated lift force, which was in the z direction, drag force in the x direction of the channel, and force in the y direction, which is mostly affected by the spin. From this, we can see trends in the way that the spin ratio affects these forces. Shown here are the graphs of lift force and drag force versus the spin ratio. The general trend observed from the data is that drag force increased or became more negative because the drag opposes the flow as spin increased, and the lift also increased, but spin peaked at a spin ratio of around 0.8. This graph shows the force in the y direction, which would be 0 for a straight trajectory and non-zero for a curved trajectory. As seen here, when the cylinder was not spinning, there was negligible force that would curve the trajectory, but when the Frisbee spun, there was force in the positive y direction, which is to the right. This is due to the Magnus effect, which means that when the Frisbee spins and the fluid flows around it, there is higher pressure on one end and lower velocity, and on the other end there is lower pressure and higher velocity. In this case, there is an expected pressure increase at the bottom of the Frisbee, causing lower velocity at the bottom and higher at the top, influencing the force in the y direction. This effect is visualized by these pressure graphs. On the left, there is no spin, and on the right, there's a spin ratio of 0.8. It can be seen that the left graph is symmetrical, while the right graph has almost 4 times the pressure on the bottom, the right side of the graph, than the top, the left side of the graph. Here we have the velocity profile for the Frisbee that doesn't spin, and it is pretty symmetrical. In this graph for the spin ratio of 0.8, it can be seen that the wake behind the Frisbee is slightly asymmetrical, which is another way to visualize the Magnus effect and predict that the trajectory of the Frisbee will be curved. To validate the model, other studies were looked at, including a study done on the spin ratio of the Frisbee that observed similar trends on force components when increasing the spin ratio.